Hello, so today we're just going to be reviewing some modular arithmetic properties, and we're going to be moving into a new concept, which is Fermat's little theorem, right? And this Fermat's little theorem is very important to modular arithmetic. So first, we're just going to have a quick review. So when I have a number like 5 here, and that's congruent to x mod 2, x does not represent necessarily the remainder when 5 is divided by 2. It can be any number where if you were to move up or down in intervals of 2, you'd be able to achieve this number of 5, right? So if I have a number like 1 here, then I'd be able to add 2 twice, and I'd be able to get 5. If I have a number like -1, I could add 2 3 times and get it to 5, right? But if I have a number like 4, I'll never be able to reach 5 because no matter how many times I add or subtract 2, I'll never be able to reach that number. So you can see how this modular arithmetic property is applied. Okay, so from here, we're just going to get into a quick question. So this may seem very daunting at first, but you may want to pause here and try to solve the question, just using what you have learned with modular arithmetic. Yeah. Okay, so now that you've had a chance to solve it, we're just going to show you how to solve this, right? So there's an interesting property with modular arithmetic, which is that if I have a number here, and that's congruent to x mod 7, I can replace this number with this number if it holds true, right? What can x be here that allows us to evaluate 6 to the 120 very easily? We can have -1, right? So we can actually replace 6 with -1, because technically, when it's congruent, right, we're saying that this number, we're trying to find the, I guess, remainder, or the leftover number when you add or subtract intervals of 7. So when we have this congruence, we can actually change or substitute the number 6 with a different value that still holds true for the same, I guess, number of 7s. So to explain this quickly, right, if I have 6 here and I have a -1 here, I can actually substitute -1 into there, which is an interesting property of modular arithmetic. It's caused by this what is equivalent to, not just equal to, right? So I put this -1 here. I get -1 to the 120 minus 1 is congruent to x mod 7, right? And -1 to the 120, -1 to any even power is always going to be 1. 1 minus 1, which is on this side, is equal to 0. And that must mean that x must be equal to 0, and the remainder when this big number is divided by 7, right, must be 0. So that's the answer to that question. Basically, you're able to substitute any number that still holds true for the same mod 7 or mod p property, right? Okay. We're now going to move in to Fermat's little theorem. So Fermat's little theorem basically states that if I have one mod p in any case, right, p can be whatever it needs to be, right, then this holds true for a to the p minus 1, right? P and a must be relatively prime, meaning that they have no common factors other than 1. So 7 and 5 would be relatively prime, but 10 and 5 would not be relatively prime because 5 is a factor of both of them, right? 7 and 5 do not have any common factors. It doesn't need to be prime numbers either, right? 4 and 9 are also relatively prime because they have no common factors, right? 2, 2, 3, 3. So in this case, they would also be counted as relatively prime. So under this formula, what we can see is a very nice property. Let's say we have a number 1 mod 7 is congruent to a can be whatever number, it has to be relatively prime. 111 to the 8th, right? You'll see that this actually holds true. The remainder when 111 to the 8th is divided by 7 will actually be 1, right? That you'll be left with an interval of 1 or starting point of 1 when you add a certain number of 7s. So we can use that definition. And we're going to be trying a practice problem with this formula. So basically, we want to find the remainder when 8 to the 2021 is divided by 5. What's the remainder of that number? We'll give you some time to solve it. All right, now that you're back, we can actually apply Fermat's little theorem here. So we're trying to find the remainder when this big number is divided by 5. How do we do this? Well, since 8 and 5 are relatively prime, let's try using Fermat's little theorem, right? Let's try 1 mod p, which would be 5 in this case, because 5 is the number we're dividing by, must be congruent to 8, which is relatively prime to 5, to, let's say, it has to be the fourth, because it has to be 5 minus 1, right? So the fourth. So 1 mod 5 is congruent to 8 to the fourth. So that means that whenever we divide 8 to the 4 by 5, we're going to result in a value of 1. How can we represent this equation differently? Well, we have 8 to the 2021, 8 to the 2020 times 8. This is equal to 8 to the 2021, right? And 8 to the 2020 is actually divisible by 8 to the 4, meaning that this number can be represented as 8 to the 4 to the 505, if I'm not mistaken, right? And what have we learned? Times 8, sorry. And what have we learned with this property? 8 to the 4 is equivalent to 1 under this operation, under mod 5. So that we can just substitute 1 into here, 505 times 8. And that gives us a final value of just 8, right? And what's the remainder when 8 is divided by 5? Well, it's just 3, isn't it? So this is like a really easy way of breaking down a really hard problem that you probably wouldn't be able to solve by hand. This will take you probably hours. And you're able to apply a very cool theorem here, use special properties, and through that, you get your answer. Thank you for listening.